Welcome to the Computer Science and Engineering Tuesday Colloquium. I'm delighted this afternoon to introduce Dan Grossman. Dan came to the faculty in 2003, and his research area is programming languages. A little known fact about Dan you can take away from this talk is that he doesn't eat broccoli. It's important. And some of you know he's a hockey player, and tonight he will be in Renton at 11 o'clock on the ice, and probably the only guy who will have prepped for tonight's game by giving a talk on software transactions. So go ahead.
All right, thanks, Larry. It's nice always to present in front of the hometown crowd, if for no other reason than I can actually make it to my team's game tonight, which I wouldn't be able to do if I were somewhere else. Today I will be talking about software transactions, which are a very hot research topic in the programming languages community, the architecture community, the parallel programming community, because a lot of us believe that they can make it easier to write concurrent programs using threads and shared memory and this sort of thing. But today's talk will be an overview of the research done here at the University of Washington in our research group, and all of that research has really been done from a programming languages perspective. And you'll get a sense of what I mean by that through the talk. From this perspective, I would say that a software transaction, or an atomic block, which is how it often looks in a programming language, is just a synchronization mechanism. You're more used to synchronization mechanisms like locks and condition variables, and the difference is that a software transaction is harder to implement, but that's my problem, and easier to use, which should be good news to you. So to kind of explain in a nutshell how they work, I have some code here with the lock-based version on the left and the transaction version on the right. And I'm just imagining some Java program where I have some bank account class where the fields of that bank account might be accessible for multiple threads. So we need to synchronize access so that our program is correct. And the way you might do it in the lock-based world is, in case you've never seen Java, synchronize just acquires a particular lock, whichever one you specify, at the left curly brace and releases it at the corresponding right curly brace. That's exactly its semantics. It's a lock acquire, lock release. In the transactions world, we don't specify any particular lock or locking protocol. We just say the stuff between the left curly brace and the right curly brace has to execute as though there's no interleaved computation from another thread. Now we're going to leave it up to the language implementation to make that false, to have as much parallelism as it possibly can while still maintaining this illusion. Okay? So a lot of people are really excited about this, and I should sort of set the stage by telling you why people are excited and what I'm more excited about. So people think that software transactions are a good idea, but one reason is that they're good for software engineering. That it makes it a lot easier to avoid a lot of the concurrency problems that are so common in concurrent programming, like deadlocks, race conditions, this sort of thing. And that's what certainly has me excited. Other people will point out that they can also be good for performance. And the reason is that locking tends to be very pessimistic. You acquire a lock because you might do something, whereas in the atomic world, we're going to be very dynamic. We're going to have parallelism unless there's an actual memory conflict between what this transaction is doing and what other things happen to be doing at the exact same moment in time. But I'm not really going to focus on that as much. And then there's an orthogonal dimension, which is what sort of research should we be working on? Should we be designing new chips, new multi-core hardware with transactional support built in? And the answer is maybe, for my opinion. A lot of people are working on that. Or should the research be focusing on software support, understanding how we can in software support this sort of synchronization mechanism? And that's where I focus. I'm not a hardware person. And I think the biggest reason is even if the underlying hardware had transactional support, there's still all the work we have to do to get you from, say, Java, or your favorite language, down to the hardware. And these things just operate at very different levels of abstraction. There's no way we're going to keep the compiler out of the transaction business. On the other hand, we might keep the hardware out of the transaction business. Time will tell. But what most people are coming around to believe is that the hardware support will be so-called best effort. It will try to execute transactions really fast. And if it can't execute them at all, it'll throw up its hands and make the software do it. And if that's the case, we're going to need the software solutions anyway. Okay? And by the way, lest I remind you, there are going to be billions of chips out there without transactional support. And you don't want to commit to certain kinds of hardware when you write your high-level application. Okay. So what I want to do is not spend the next hour talking about the low-level fancy data structures and algorithms that bring transactional memory to life. It's obviously necessary that you have clever algorithms to do this, and my colleagues and collaborators at other universities have been working really hard on this. But perhaps less obvious, but no less important, is all the other stuff you're going to have to do if you're going to add this to next-generation programming languages. And that's what we're going to focus on, and this is really where the programming languages aspects come through. And the first is to absolutely make sure we have the motivation right, to really understand as essentially as we can why transactional memory is better than locks. Because if we don't understand that, we're not going to design the right thing. Okay, so we're going to spend plenty of time on that, and if nothing else, you'll leave the talk well motivated on why we're going through this enterprise. And having done that, now we can design proper programming languages. And I'm going to argue that you're going to need a rigorous high-level semantics to do that. We have to understand exactly how transactions behave, as well as how they interact with the rest of the programming language. And only then will I allow us to talk about implementation. And there we also have to ask the question of how do things interact with all the fancy stuff already going on in our compilers. And perhaps more interestingly, what new optimization opportunities and responsibilities is the compiler going to take on in a transactional world? And remember, the next desktop computer you buy will probably have multiple processors in it. And if you want your applications to run faster than they did on your 5-year-old computer, you want answers to these questions. Okay? So I'm going to aim for breadth over depth and basically cram about 5 talks into one. But I'm going to try to not speed up. So hopefully this will be the speed that we get to go through for the entire time. And focus in the first part of the talk on language design and semantics issues. So I'll start with sort of my favorite example where transactions rock and locks don't. But then argue that examples aren't good enough. That if we want to figure out the essential advantage, you can't just stop with, ooh, look at this small example where transactions are really useful. And that example has to do with garbage collection, which might be a little surprising to you, but you'll see the connection when we get there. Then I'll move on to semantics and talk about what I think is the most important open issue on the semantics front, which is what does it mean when there's a race between transactional code and non-transactional code? And this is usually known by the strong versus weak isolation debate, and we'll talk about that. And then I'll largely take a pass on all the work we've done on how transactions interact with all the other language features. Just say a word or two about that. And then in the last 15 minutes or so, we'll put our implementers hats on, and I'll show how you should implement transactions when you're only running on one core. That's a much simpler case, and when you have a simpler case, you should optimize for it. But it's also a nice segue into the work we did in the multi-core case. Because when you go multi-core, you end up having a lot of overhead you don't need in the uniprocessor case. And we've worked on optimizations that eliminate not all of that overhead, sometimes you need it, but eliminate it when you can prove you don't need it. And then at the end, I'll talk about some ongoing work, basically a sales pitch on the work we're doing on allowing parallelism within a transaction. Okay, so now I will launch into my favorite example of why locks are really not that good a way to build large concurrent shared memory programs. So the idea is still this bank account idea. I have a bunch of bank accounts. They might be accessed simultaneously by different threads. So I need to keep the data separate and in critical sections so that I don't have race conditions that break my application. So when I design version 1 of my system, I decide I'll have a separate lock for each bank account. So as I write my deposit method or withdraw method or balance method, I'll just grab the lock corresponding to that bank account, execute some code, and then release the lock. And that all works great. There's no problem with that. But my manager comes along and says, for version 2.0 of the system, we really need this transfer method. It's going to move some money from one account to another. And oh, by the way, I want to do that transfer sort of all at once, so that some other thread that, say, was trying to total up all the balances in the bank wouldn't get the wrong answer. Okay? Now, the sequential logic here is no trouble. It makes a few calls to balance and withdraw for the other account, checks against the maximum transfer amount, and so on. It's the synchronization that's a problem. If you do the naive thing and grab the same lock you did for deposit, withdraw, and balance, you have a classic race condition. And the reason is that you checked the balance of the from account, and then later you did the withdraw. And because you don't hold the lock for the other account, in between, the balance might change. So the check you did could be invalidated. So you might say, I know how to fix that. I'll just grab the other lock too. But now you have a classic deadlock situation. It's easy to see here in the sense that if you had one thread that was trying to transfer money from account A to account B, At the same moment another thread was trying to transfer money from account B to account A, you can get in a situation where each of them holds one lock and is waiting for the other one. It's a classic deadlock. By the way, the previous version of the code had the exact same deadlock. You just couldn't see it as obviously. Okay? So now what do we do? Well, the answer, if you're actually doing this, and Java's standard library with its string buffer class had exactly this problem, is you basically throw up your hands. If you're going to write this transfer method correctly, you're essentially going to revisit your entire banking application, install a partial order on your bank accounts, and insist that you acquire the locks according to that partial order. And good luck with that. So let's try it again from the transactional world. So in version 1 of the code, we just use atomic to make sure that, yes, please, Tom.
Why couldn't you just compare this and from?
Yes. You could do that and always acquire them in the correct order. That's easier said than done in Java, for example. You can't take their address. Objects get moved around by the garbage collector. You could hash on them, but sometimes they conflict. Actually, the best solution, I think, is to have a language mechanism that lets you present all your locks up front and do a little two-phase protocol right there to grab them all, which would be enough in this example.
So the problem is
Sure. Yeah. But there are good reasons to not expose the addresses of objects. Right? So we could revisit all those reasons and resolve that trade-off. Okay. Okay. So transactionally, version 1 works fine. We just replace our synchronize with our atomics. And then we go to write version 2. And if you don't do any synchronization, you have a race condition. Now, I want to be very clear on this. Right? Transactions do not make the problem trivial. You can still have race conditions. You still can have code that is correct sequentially and wrong in parallel. Okay? Let's be clear about that. But if you put the critical section in the right place, not only is your code now correct, but it has a remarkable amount of parallelism. We're going to ensure we have parallelism as long as the memory that this code accesses is distinct from whatever the memory accessed by whatever is running in parallel. So we'll basically have exclusive access to these two bank accounts, but compared to a solution that had, say, one lock for the entire bank, we expect to have a lot more parallelism. Okay, so when you see examples like this, and a lot of papers start with this stuff. Yes, Tom?
So there's no inherent addition to parallelism in your example compared to a good implementation of lock.
Yeah, and in some sense, a good right. There's two answers to this question. Did you mean by the programmer or by the underlying implementation of lock?
Well, I mean, you're just in the compiler, assuming there's no hardware support, you're just doing what a good programmer would do. But you're doing it automatically.
Absolutely. I could not agree more.
So there's no inherent notion of it's parallelism preserving more than enhancing the amount of parallelism you have, right?
I think that's correct. Yeah, absolutely. And I think it's fair to say that I'm not necessarily interested in beating well-designed, low-level, fine-grained, manually written synchronization code. I'm not trying to be faster than that. Exactly. That's exactly it. Yep. And it's a wonderful segue, because I couldn't agree more, into, these examples are appealing, but what essentially is going on? And that's a big part of the essence of what's going on. But from a programming language's perspective, the way I like to think about it is that transactional memory is the garbage collection of shared memory concurrency. All right? So if I were writing an SAT, I would say transactional memory is to shared memory concurrency as garbage collection is to memory management. Now this is a great sales pitch, but I'm not a used car salesman. I'm a programming languages researcher. So I have backed this up with an essay that explains this connection on technical terms for about 5 pages. And I want to give you a flavor of what that is about, so you'll go off and read the essay after the talk. Okay? So to do that, let me tell you everything you have to know about garbage collection. 40 years of research in one slide. Okay? All right. So it's the memory management problem. When you need some data, say you call malloc in C or new in Java, you put it in the heap. And when you're done with that data, you deallocate it so that you can reuse that heap space. And the whole memory management problem is when should you deallocate something? If you do it too soon and you use the object after you deallocate it, you have a dangling pointer and your program behavior is undefined. So fine, you can solve that by never deallocating anything, but then you'll run out of space, or at least use more space than you need to, and you'll have poor performance. So what garbage collection does is automate this for you. It says, don't you worry about deallocating things. I'll do it for you. And the way I'll do it is I'll start with a set of roots. Just think of this as the pointers on your stack. And I'll see what objects they point to. And I'll continue transitively to what objects are pointed to by them and so on. Those are the blue ones in my picture. And I'll keep those around. But anything that's unreachable, you're definitely not going to use again, because you can't possibly follow pointers to get to it. So I'll deallocate those. And those are the red blocks. And the real thing I want to emphasize about this is A, it's automated, and B, it's an approximation. Just because something is reachable doesn't mean you will use it again. It's the converse. If something is not reachable, you definitely won't use it again. So this is a classic approximation. The other thing is that garbage collection is established technology with widely accepted benefits. Even though this is not just like a factor of 2 approximation. This approximation can do arbitrarily badly compared to manual memory management code. All right? And you cannot always ignore how GC works. You need to understand reachability at some point when you're programming in a high-level language. And it continues to be an active research area. We haven't written the world's best garbage collector yet. We're continuing to write better ones. And yet, a lot of people rely on garbage collection every day. So I want to basically argue that transactional memory can be good technology, even though it has limitations. And I'm going to do that by telling you some things about memory management, and then telling you the exact same things about concurrency, and just switching around the nouns as I go. OK, so one way to think about memory management is that it's a hard problem because there's a fundamental tension between correctness and performance. The correctness problem is that if you make the lifetime of your objects too short, you can have dangling pointers, and your program makes no sense. On the other hand, if you make the lifetime of your objects too long, you can lose performance by wasting space or eventually even running out of memory. So when you go to do this manually, what you end up doing is coming up with some kind of whole program protocol to keep track of the lifetime of your objects. One particularly simple one you may have heard of is reference counting, where for each object you store with it a manually maintained reference count. And if that reference count drops to 0, you can deallocate the object. And if you do this, you have a problem with cycles, because if you have a cycle of objects, you'll never deallocate the memory. Okay. So one way to think about the concurrent programming problem and why it's hard is that there's a fundamental tension between correctness and performance. If you make your critical sections too short, you have race conditions, and your program produces the wrong answer. On the other hand, if you make your critical sections too long, you have a performance problem because you're giving up parallelism. And the extreme, you might deadlock, and none of your critical sections are able to complete. So when you go to do concurrent programming with locks manually, what you end up doing is using some sort of whole program protocol to keep track of what thread can access what. One particularly simple idiom you may have heard of is locking, where you associate some lock with each object in your program. Now, if you do that, you do have to worry about lock acquisition cycles, or you'll never complete a critical section. Going back to memory management, another way to look at the problem is that it's inherently non-modular. By that I mean if I have a caller and a callee, I'd really like to reason about that interaction based on the arguments passed and the result returned. But in the presence of manual memory management, you can't do that. You also have to know what memory the callee and the caller access, even if you're the other guy. Otherwise, the callee may deallocate some memory the caller still needs, or vice versa. This is even worse as you go to evolve your software and change it over time, because if you change the lifetime of a piece of memory, it can often require wide-scale changes to your code to update the bookkeeping for memory management. And the fundamental problem of what's going on here is that correctness requires knowing, at each point you're thinking about deallocating an object, whether it will be used again in the rest of the program. So another way to think about the synchronization problem is that it's inherently non-modular. I want to reason about caller and callee just in the arguments passed and the result returned. But instead, I end up having to think about exactly what memory the caller and the callee might access, even if I'm on the other side. And that's because if I don't know, then I might release some lock that the other guy needs held for the access it's going to, the memory it's going to access. And this problem gets even worse as you go to evolve software and change it over time, because if you make a change to what memory some critical section is accessing, you may need to make wide-scale changes to your code to make sure that the right locks are available. And fundamentally what's going on is that for correctness, you really need to decide at each point in your program what might get accessed in parallel. Okay? So getting back to Tom's point, the solution here, and I'll do the memory management side first, is to take that whole program protocol and hopefully get it out of the application code and into the language implementation. That way it can be written once by experts who spend their entire life thinking about how to write garbage collectors. The trade-off is they don't know anything about your application, so it's a one-size-fits-most solution. But thanks to being inside the compiler and the runtime system, they have access to some very useful internals for doing this well and doing this conveniently. Make no mistake, though, a garbage collector absolutely relies on subtle whole program invariants. For example, it tends to add extra bits to the beginning of each object, and the meaning of those bits change at different points in the execution of the garbage collector. It also relies on certain properties, like when you allocate a new object, none of your existing objects point to it yet. And that's a nice property you can exploit for performance. So the key thing about transactional memory is that it takes that whole program protocol and it lifts it out of your application code and puts it in the language implementation, where it can be implemented by experts who spend their entire lives thinking about how to implement transactional memory efficiently. They don't know anything about your application, so it's one size fits most, but it's extremely convenient that they're inside the compiler and the runtime. Make no mistake, though, transactional memory really does use subtle invariants. For example, it puts extra bits at the beginning of every object, and those bits have different meaning at different points while a transaction is running. It's also the case that when you create new objects, they're thread local, and no other thread points to them, and still some subsequent computation occurs, and that's something that can be exploited for performance. So the whole point, and the details don't matter, is to understand that these problems and solutions have very similar structure. There's a tension between correctness and performance. We automate, and there's various aspects of that automation that are analogous, like optimizations relating to new objects. But I want to tell you one more thing about the analogy, which is how they are also approximations in very similar ways. So let's start with when garbage collection is a bad idea. Garbage collection is a bad idea when reachability is a bad approximation of what memory you need. All right? It's always an approximation, but when it's a big approximation, you shouldn't use garbage collection because you'll consume too much memory. Now, if you're stuck in a garbage collected language and reachability is bad for your task, you should use this feature called weak pointers, which are fundamentally pointers that don't count for reachability. You may not have heard of them, and if you've heard of them, you may not have used them, because they're generally only used by expert programmers for certain well-recognized idioms, like using a software cache. I would also point out that if you really want manual memory management in Java, go right ahead. You can encode object pooling, basically managing your own buffers of objects, on top of garbage collection, so I can't protect you from yourself. We can also ask, when is transactional memory a bad idea? Well, it turns out it also relies on a fundamental approximation. And that is that if there's a memory conflict between two transactions, then they cannot run in parallel. That's not necessarily true. It's a conservative approximation of what can run in parallel. So if that's a bad approximation and you're stuck in a world where transactions are your synchronization mechanism, there's actually something you can use. It's called an open nested transaction, which is essentially a set of memory accesses that do not count for conflicts. All right? That said, you've probably never used them. You might not have even heard of them. That's because they're best used by experts for certain well-recognized idioms, like two transactions that both generate unique IDs by incrementing the same counter. It's a memory conflict, but you don't need to abort a transaction in that case. I should also point out that in the extreme, if you really want locking in a world with transactions, you can code it up on top of transactional memory, and you'll lose all the advantages of transactional memory in the process. So here's 10 lines of code you don't need to understand, other than to realize that it implements spin locks using transactions. It is not surprising that one synchronization primitive can be implemented in terms of another. This is a classic sort of operating systems homework exercise. Okay? All right. So the analogy keeps going in terms of the implementation techniques or whatever. I will point you to the essay for the rest of it. But what I want to sort of leave you with is that this analogy exists and it's useful. The reason why it's useful is, first of all, to remember that transactional memory does not have to make concurrent programming easy. It just has to make it easier. And the second is, we have a lot more experience with garbage collection than we do with transactional memory. So I would like to leverage, to the extent I can, what we've learned in the memory management space to understand the design trade-offs in the concurrency space. Okay, at least hopefully now you think transactions might be convenient. And now I want to tell you about some of the deeper work we did on language semantics. Tom?
Are there other examples where it's, I mean, there's clearly a bunch of cases where people avoid using garbage collection.
Yes.
Say most of the software industry.
Right. I think that's disputable, but yes.
Are there, depends on how you count, I guess.
Yes.
Are there, do you see that there'll be similar cases for concurrency?
This gets us out of sort of the technical issues and into speculation on the industry. But one of the things I would argue is that, you know, the proponents of garbage collection were unfortunately decades ahead of their time. And it is quite likely that similar things will happen with transactions. Yeah. Scott?
So I understand when I'm programming with locks, the trade-offs in terms of performance and when I use them. What is the model I have as a transaction memory model user of I don't want it too big and who's going to conflict and how I get parallelism out of it?
It is exactly memory conflicts. Two transactions should not be run at the same time if they may access the same memory and at least one of those accesses is a write. So if you want the parallel speed up, you need to try to avoid that. One way to do that is still to keep your critical sections short. That design constraint has not changed. All right. So now we have to talk about semantics. And the big thing we have to talk about that's been confusing a lot of people working on this stuff is what if there is a race condition between transactions and non-transactions? So I have a simple example here where y starts 0, and I have a very simple transaction on the left, that by the time it finishes running, x will hold 3 and y will hold 3 because of the y equals x at the end. So the question is, if some other thread is running and it tries to print out y, what might it print? Well, it clearly can print 0 if it runs first, and it clearly can print 3 if it runs second. But under what's called strong isolation, those are the only two possibilities, because the transaction on the left really is isolated from all other computation. But that can be expensive to implement. So people like to say, well, if there's a race with non-transactional code, then maybe we should allow some additional possibilities. Maybe the print can print 1 because it can actually observe the intermediate state of the transaction. Maybe it can print 2 because it can actually interfere with the transaction via the assignment to x. Or maybe it's like a buffer overflow in C and it can do anything, like print 5577. So we can have this argument, and smart people can disagree on which of these possibilities should be allowed. But there's this big misconception that sort of these are the only problems. That the only time you have a problem is when lock-based code would have exactly the same data race. So what I want to do is show you that matters can actually be worse. This is probably the best known example of what's called privatization, but it turns out there are several examples where lock-based code works and transaction code under weak isolation, meaning the way published papers have done transactions, don't work. Okay? So in this example, I just have one global variable pointer. It points to some object that has two fields f and g. If you're a C programmer where you see dot, think arrow. Java's dot is C's arrow. And this is lock-based code. So we have some invariant. I'll keep it very simple. Say that the two fields are equal. So the critical section on the right just increments both fields. Since it holds some lock while it does it, that should be OK. More interesting is the code on the left. What it does is it privatizes the object. It sets some local value r equal to the pointer, and then changes the contents of pointer to point to some other thing. Having done that, no one can mess with the object that's now privatized. So even though I check does r.f equal r.g out while I don't hold the lock, this assertion should hold. This assertion cannot fail in a language like Java. Unfortunately, a lot of implementations of transactions allow it to fail. I'll tell you why, just because I don't want to leave it mysterious, but the details don't really matter. What happens is, the way it's implemented, I'll give an eager update example, by the way. There are systems that work differently, but they still screw up this example for a very different reason. So in eager update, what we do is we update the memory as we're running. But if a transaction aborts, it undoes what it did. It goes back to all that memory and puts it back to the old value. So the transaction on the right here, say, runs halfway. So at this point, it's incremented the F field and not the G field. And here's what I want you to realize. It has written to the F field, but that pointer space, it's only read it. It hasn't written it. Okay? So now if I go and run the transaction on the left, I go ahead and privatize the object. I set pointer to something else, and I get right to the curly brace, and I say, can this transaction commit? And the answer is yes. Okay? It has not written to anything that another transaction has written, and it has not read anything that another transaction has written. Now, once this guy commits, the other transaction must abort, okay? Because there actually is a conflict, but it's going to do that later. And in the meantime, we run this non-transactional code and the assertion fails before the code on the right ever gets a chance to undo the half of the transaction that it did. Okay? So that's the way the world works, unfortunately. And we can ask ourselves a question, which is basically who's to blame. Right? Is the code on the previous slide wrong, or is the implementation of transactional memory wrong? We can point the blame wherever we like. We can also ask the question, how many other examples like this are there? Is it just privatization? Or are there a bunch of coding idioms that work with locks and don't work with transactions? And how might we restrict our language, say with a type system, to make sure that all of those distinctions go away? And what I'd really like to know is, can I give programmers a very simple model, like Scott wanted to know, about how transactions behave without having to go into the implementation like I did for you on the previous slide? And in all of these cases, I would say, and I am somewhat biased, that unless you're doing programming language semantics, you're not going to be able to answer these questions. We're fundamentally in the business of defining what languages can and cannot do and what it means for an implementation to be correct. So we wanted to answer these questions. So what we did, this is work I did with Kate Moore, who's a graduate student here at Washington, is we defined some formal operational semantics for a collection of very similar languages. What we did is just vary from one language to another how isolation worked. And that would really let us study the differences. Now, we also wanted to be very high level so I could give programmers a simple view. So in these models, we made one simplifying assumption, which is that the program state never had more than one transaction that was live at once. That is not how you would implement transactions, but it's great for a language definition. Okay? So you let the parallelism be an optimization, if you will. So all you do is you have some program state in each of these languages that say has a bunch of E's. Those are the threads. Those are expressions that are going to run in parallel. You have some H, which is just a mapping from addresses to values. That's your shared memory. H stands for heap. And you have a single A bit that tells you if anyone's running a transaction or not. And then the way operational semantics are, you just have a bunch of textual rewriting rules from one program state to another. And that green arrow is the only thing that really changes from one language to the next, or one isolation definition to the next. So we defined three different ones. We defined the strong language. How does strong isolation look in this formal Greek world? Okay? It says, well, if one thread is in a transaction, as evidenced by that A bit, then we'll rig our rewriting rules so that no other thread can touch the heap or enter a transaction. Again, not how you would implement it, but a fine semantic definition of what it means to be a transaction. It appears that you have exclusive access to the heap. A weaker definition that corresponds to how locks work is to say, all right, I'll call this weak or weak one lock. If one thread is in a transaction, I will let non-transactional code access the heap. So race conditions are still a problem, but I won't let anyone else enter a transaction. So different transactions will still be isolated from each other. And then I have a third language, which I'll call weak undo, that starts with weak one lock, but it adds one other little thing that says a transaction can run part of the way, flip a coin, have it come up tails, and say, I'm going to abort, undo my changes, and restart later. Okay? So this gives us a family of languages. We have 3 different languages, all using the same syntax, but subtly different semantics. And now we can actually study how different family members differ, and we can define and prove conditions under which the different languages are indistinguishable. I should also point out that if you think semantics work is dry, you're not alone. So when you go to do this work, it helps to have a catchy name. Since we have multiple languages all dealing with atomicity, we call it the Atoms family. And if you didn't chuckle, just be proud that you've watched less bad American television than the people in the audience who did chuckle. Okay. All right. So now that we have these different languages, we can do what semanticists do, which is prove theorems. These are important theorems, but these ones are really easy. This entire page took us like an hour. Okay? So the first is that every program behavior that's possible in the strong language, take a program, however it behaves in strong, it can behave the same way in weak one lock. And similarly, this is the third theorem, however a program can possibly behave in weak one lock, it can behave in weak undo. Weak undo lets you abort, but it doesn't ever say you have to. That's all the third theorem says. The converses do not hold. So the second theorem says that weak one lock introduces behaviors that are not there under strong, namely race conditions. And perhaps more surprising is that when you add this undo mechanism, you actually get behaviors you didn't have before. And that's one of these gotchas we didn't anticipate when we defined transactions a few years ago. Okay? The database people would have told us that we should have, but we're not as smart as them a lot of the time. Okay. All right, so here are the hard theorems. They want to go the other way and make those converses true, but they're not true in general. So we need sufficient conditions to make them true. And what we do is we define a type system that ensures the following. It says if you have some mutable memory, then it has to go in one of two sides of a partition. In one side, we only allow that memory to be accessed inside of transactions, and in the other, we only allow that memory to be accessed outside of transactions. Now that's a very strong requirement. It deems our privatization code wrong. But at least we can prove that under that strong requirement, all of these distinctions between the languages go away. That's exactly what we did. We proved that if a program type checks, then any program behavior it has under strong, it has under weak one lock, and any behavior it has under weak one lock, it has under weak undo. So to summarize 4 months of Greek letters in one picture, let me walk through again how these languages are connected and how you can prove them. So I have these 3 languages, strong, weak one lock, and weak undo. If you can do it in strong, you can do it in weak one lock. That's trivial. Just don't interleave. If you can do it in weak one lock, you can do it in weak undo. That's trivial. Just don't abort. When you go the other way, you must assume the program type checks, i.e. it has this partition. And to prove that anything possible in weak one lock is possible in strong, you have to argue that since the memory is disjoint, you can commute operations until it appears that the whole transaction appeared at once. This is a classic serializability argument, which is already common in other areas of computer science. But when you go to do weak undo and weak one lock, it turns out there's 2 things going on. You have this abort mechanism, which you have to prove works correctly. And you have this commuting business, which is really kind of complicated by the abort mechanism. So what you do is you do a proof technique, which says, let's not prove weak undo equivalent to weak one lock. Let's prove it equivalent to some new language that has the strong isolation of strong, but still has the abort mechanism. And now that arrow is exactly the previous arrow, where we made the serializability argument, with a few new cases for the new rules for abort. And now this last arrow is not so hard. You just have to prove your abort mechanism is correct. And thanks to transitivity of equality, we're all done. Okay? So that was good. Okay. All right. So all I really want you to know are 2 things from this part of the talk. First, weak isolation has far more surprising behavior that is not just race conditions from lock-based code. And the second is that formal semantics lets us model the behavior and prove theorems that tell us we've at least got a handle on what the source of the problem is. Okay? And so really our goal here is to come up with a type system. The one I showed you is sufficient but awfully restrictive, so that our language can have strong isolation semantics, but our implementation can do the weak thing that we want to for performance. Okay? The other thing you have to do before you go and buy a programming language that has transactions in it is you have to figure out how it interacts with all the other features your modern programming language already has. And while I'm not going to have time to tell you about all those, I did want to give credit where credit is due. Yes, Tom.
So you had said that earlier that the advantages of transactions was that you didn't need to have a global understanding of your synchronization behavior program.
Yeah.
But now you've introduced type theory as a way of providing a global constraint on the behavior of your program.
I think that's right. You're right. And it is absolutely true that if you had a program that type checked, and then as you maintain it, you change something, it may require sort of cascading changes to get it to type check again. But at least we have the static support to check that we've made all those changes. I don't think I can make a stronger rebuttal than that, which is exactly the point. That's right. And also speaks to the fact that there's been a lot of overselling on transactions. And I think the work we've done has been worked very hard not to oversell. And so, for example, we've said, hey, you need this static property for things to work correctly. And if that static property is a global one of your program, well, then so be it. Okay. All right. So what about everything else? What if you're inside a transaction, you make a foreign function call out to C? Well, that's a hard thing to deal with, but we at least have a practical solution that Mike Ringenberg worked on a couple years ago. What if your transaction throws an exception? Or if you're in a language like Scheme and it uses something called call CC, or call with continuation. Well, you better have an answer to that. These languages already have other features. You have to deal with them. One of the things Kate looked at in our formal work is what if you want to create a thread inside of a transaction? What should that mean? Is it part of the transaction? Does it run after the transaction? You need a story like that. And Ben Heidman, who is an undergrad here, now down at Berkeley, dealt with class loading issues that you probably don't want to know about. But Java has class loading issues. And something that is still open in the source of a seminar we're running this quarter is what do transactions do to your memory consistency model? We have answers even if we don't love them for locks. I don't think we even have answers for transactions. So I consider that open. Okay. All right. As promised, 10 or 12 minutes on implementation. And I'm going to start with the simple case, which is what if you wanted to implement transactions, but you knew you were running on a Uniprocessor? Or you can run on Multicore, but you're only allowed to use one of the cores. Okay? So let me start with why is this interesting at all? Well, let me remind you that my grandmother still has a Uniprocessor, and yours might too. Many language implementations don't allow true parallelism. But perhaps more interestingly, just because you have 8 cores doesn't mean your app has been assigned more than one by the operating system. And whenever you're only running on one core, don't use a fancy implementation when a simpler one will do. So here's the simple implementation in just a couple minutes. What you do is you just start running the transaction, but as you run, you log the writes. All you have to keep track of is what have you written to and what did it have before you did the write. And then if the scheduler preempts you, before you go and run somebody else, undo your updates. Try the transaction again in your next time slice. And you want to do a little code duplication so that you're not constantly testing, do I need to log, do I need to log? You have 2 versions of your code, one that knows to log and one that knows not to. So how might this work? Well, I have a little example here. The function h starts running. We start a transaction. Aha, we assigned it 2. So we just build up a little LIFO log that says, well, y used to hold 0, so I'll put in my log the address y and the value 0. And then as it continues running, you can make function calls. You can do whatever you want. But as you write to memory, you keep logging the previous values in your log. If you get preempted before you hit the right curly brace, you just go through your log in reverse order, doing the assignments back to the memory how it was. Set your program counter back to the beginning so you can rerun the transaction when you start your next time slice. And that's it. If, on the other hand, you get to the end of the transaction before your time slice is up, you're done. Drop the log on the floor. No harm. Okay? So it turns out the rest is engineering to keep the log small. You want to make sure, the key thing that's going on here is that our log only has writes in it. That might seem obvious to you, but it turns out in the multiprocessor setting, you do need some bookkeeping for your reads as well. And a lot of programs do a lot more reads than they do writes, so this is really the key of the issue. There's some other things, like if you allocate memory after you enter the transaction, you don't need to log updates to that memory. And there's issues like you don't need to log something more than once. For example, that second assignment to y is a complete waste of time. But what we typically do is just some good engineering to start off by just logging everything, because that's faster than detecting duplicates. But if the log grows too big, you fail over to a hashing scheme. So we wrote papers about this. They have performance charts. They're incredibly boring. Because this is like so fast, you're like strained to come up with something where you can even measure the performance of it. And the reason is programs do a lot of reading and writing memory. Sometimes in transactions, sometimes out of transactions. And in 3 of those 4 boxes, we don't have to pay anything. We also have this rollback mechanism, but rollbacks are so rare you almost never pay for it. Yes?
What do you do about writes that have side effects?
Writes that have side effects, like?
printing to the screen.
Yes, external effects. You basically need to provide an external rollback mechanism that says what to do if it's abort. You need to buffer output, things like that. Turns out the key thing that gets you is not output and it's not input. It's input after output. You can't do a round trip inside a transaction to some other process that doesn't know that it has to execute transactionally. Okay, so the lesson here is that you should special case the uniprocessor, but anyone who's built big systems already knows that. You should always special case the uniprocessor. Transactions are no exception. Okay, but there's a lot of multicore out there, and we don't get the table at the top. We have to deal with the table at the bottom, which says that in transactions, there's not just going to be write overhead for logging. There's also going to be read overhead. I'm willing to put up with that. And so are a lot of other people, and it's a good thing because we have no choice. But we'd really like to not have the overhead outside of transactions. And that's really why people implement weak isolation. That's really what they're saying. They're saying, I just don't want to pay for this. But I think semantically, strong isolation makes a lot more sense. And so what if we had overhead here? Well, we might need it sometimes, but hopefully there are compiler optimizations that would let us get rid of it. That's exactly what Steve Balanciefer and a couple other people were working on. And there's a few ways you might go. You might say, well, if I'm outside of a transaction, I'm accessing thread local data, then that can't possibly interfere with a transaction, so I'll eliminate the overhead. It's a great idea. It's an old idea. It's been researched. Another idea might be if you're accessing immutable data, you can eliminate the overhead. Also a good idea, but not so useful in Java. A third possibility is maybe your data is thread shared, and it's mutable, but you can prove that it's never accessed in a transaction. Now, if you remember the semantics part of the talk, this is exactly a static approximation of my type system. My type system enforced that this was always the case, and therefore I never needed to pay for strong isolation. Now we're taking the equivalent optimization approach. I'm saying, well, maybe I'll sometimes need the overhead, but I'll make it a compiler optimization to just automatically remove it when I can prove I don't need it. Okay? So that's exactly what we did. We ended up calling it NATE for not accessed in transaction. And what it does is it allows you to say that if you're outside of a transaction and what you're accessing is never accessed in a transaction, then you can remove the overhead. And there are some differences for reads and writes that aren't so important. Okay? But you have to know, is what I'm accessing what somebody else is accessing? And that requires alias information. In the compiler world, that's called pointer analysis. So this work does rely on a whole program pointer analysis. If we don't have all the code up front, our analysis cannot run soundly. That is the primary limitation of the work. That said, the pointer analysis we use is about as fast a whole program analysis as you could expect. It scales to 100,000 line programs if you include the libraries and things like that. If you know the jargon, it's context insensitive and flow insensitive. And what I'm skipping here is that after you do the pointer analysis, we have to run over your code 2 more times. And so it's really quite fast. Okay. I should also point out that you can keep this entire analysis separate from the rest of your compiler. I know, because that's how we did it. Steve implemented the analysis, ran it over bytecodes, emailed the results to our colleagues down in Santa Clara, who then fed it into their compiler, used the information to eliminate the overhead, and ran the programs. Okay. So here's what happened. This is an application. It's a small traveling salesperson problem. I'll show you one other graph on the next slide. Each group of bars is running the same program with a different number of threads. It goes from 1 to 16. We're on a 16 processor machine. The y-axis is time, so lower is better. And the fact that the blocks go down shows that this application does scale as you increase the number of processors. Within each block, we have several variations of the program. The black bar on the left, say, is our baseline. That's the original lock-based program before we converted it to run with transactions. So that's kind of like what some Java programmer did initially. When we switch to weak isolation, that's the next bar, the second one in each block, we pay a little overhead, but not very much. We moved it automatically to the runtime system, and it works just fine. But then the next bar jumps to strong isolation. It inserts all that extra work on every read and every write, even for the code outside of transactions. Okay, so there's a big jump there. It's about a factor of 2. The next 2 bars employ some optimizations from our colleagues down inside the compiler that I didn't talk about. We can see that they give you some help, but not very much. In fact, on 16 processors, they actually hurt you. Welcome to the world of compiler optimization. And then the last bar is when we employ our whole program pointer analysis information to eliminate the overhead. And we do not get all the way back to the performance of weak or the performance of the lock-based code, but we do pretty darn well. When we switch over to JBB, which is a transaction processing warehouse simulation thing, the y-axis is now throughput, but lower is still better. And everything else means the same thing. The story is a little bit different. It turns out that when we go from the lock-based to the weak isolation, that's where we take most of our performance hit. And going from weak to strong actually is, on this particular application, is not that much worse. But again, when we go to add our static optimizations to remove the overhead, we actually recover pretty much all of the performance difference from weak. And if you have really good eyes, you can see we actually sometimes do better. But that's because the dynamic optimizations in the compiler backend plus ours conspire very nicely. OK, so the lesson is the reason why strong isolation costs is outside of your transactions. And compiler optimizations can recover a lot of that performance difference. OK, so finally, a sales pitch for some ongoing work that Aaron Kimball is doing, even though he's not here today or even in the country at the moment, is to realize that all of the implementations out there that I know of, with one small exception, assume that inside your transaction, from the left curly brace to the right curly brace, you run sequentially. All right? There's good reasons to assume that. It makes your implementation a lot simpler. But there's this law from Amdahl that's going to sneak up on you as you increase your core count. Right? If all of your transactions run sequentially, eventually your transactions will take all your time, and they're running single-threaded. But there's no reason to do this. Isolation and parallelism are orthogonal concepts, and it makes perfect sense to allow parallelism within a transaction. Okay? Now, there are language design issues. Like now, if you're within a transaction, two different threads might need to isolate themselves from each other, and so they need transactions inside of transactions. But that's just a beautiful generalization. All right? What's less beautiful is going into the guts of a software transactional memory system and changing it to support this parallelism. And the reason is we have to do logging, and you can't have contention over your log, or you're going to give up all your speed up. So parallelizing the logging is where all the action is. I'll be honest with you, it makes it more expensive, and you probably don't need this until you have core counts, let's say, in the hundreds. But much like the seminal work on concurrent garbage collection was done years before it was needed, I'd like to believe that we'll need this eventually as well. Okay. All right. So I am essentially done. Let me again remind you that this work was completely done by a handful of different students. Let me also point out that this is like a fourth of the work going on in the WASP group here at Washington. So my apologies to Marius, Ben, Matt, Laura, John, Anna, and Sam.
So it seems like the examples you use to benchmark were pretty simple. Mm-hmm. Is that because that's as much as you have done or want to show us here, or as much as you actually could do in these systems?
It is as much as we have done. I don't have more complicated applications to show you. I think the systems are fully capable of it. It's the people working on and researching those systems failing to have the manpower to build or understand large applications that are not on their critical path, or finding suckers to use their system. And when we go to workshops on transactional memory, we sit around crying in our beer about the benchmark problem. And we're getting there. You know, this is young, immature stuff in the sense of, you know, spec doesn't have a collection of 10 applications using transactions that we can use. Paul.
You made the analogy between garbage collection for memory management and transactional memory for handling problems with concurrency. I mean, notwithstanding the fact that there are apps that end up with memory leaks and so on, it seems that the mental model required to handle memory management correctly is somehow a lot simpler for all of us than that required to handle concurrency. When I just sort of in terms of published papers, the number of published research papers which have screwed up concurrency is phenomenal, even by big names in the field. So, in some sense, you might be selling it a bit short. That's you know, the benefits of this.
Yes, it does. So the key thing that transactions do not solve, and this actually fits with the analogy, although I didn't discuss it in that part of the talk. Transactions say nothing about where your critical section should start and end. In some sense, they make it declarative. You want a critical section here? Just say it. There's no locking protocol. There's no mapping from locks to data. But you still have to get your critical sections right. And there is, I would say, by definition, no analog in sequential programming to having to put your critical sections in the right place.
You, following on from that a little, which aspects of the writing a lock-based, correct lock-based program do people actually have trouble with, other than that one of identifying the critical sections?
I think all of the above. But as a scientist, I mean, I haven't done that research. I'm not aware of sort of software engineering research that says, was it the object to lock mapping? Was it reducing contention? Was it going from coarse grain to fine grain? Was it knowing where to put the critical sections? You know, I've actually seen one workshop paper where they did what you might imagine. They took an undergraduate operating systems class and they divided them in half, and this half used transactions and this half used locks, and they claim a statistically significant result in time to finish the lab. But there's a big difference between a 20-line junior programming lab and a real application.